This video module goes over the use of the mmc.py Python module that's used to analyze MMC queuing systems. Note that we're not going to discuss queuing systems in detail, so I assume that you already have a background and you know what I'm talking about when I say an MMC queuing system. If you need a refresher, there are a couple other video modules in this series that talk about the details and talk about the mathematics and so on. So a queuing system that we're interested in, as I said, is a single server queuing system where we have entities that arrive and wait for service by a server that has capacity C. So the capacity determines how many entities can be served simultaneously. We assume that the entities arrive at the rate lambda and can be processed by each server at the rate mu. And we're interested in metrics such as the number of entities in the system at steady state, the number of entities in the queue at steady state, the time that an entity spends in the system, the time that an entity spends in the queue at steady state, the utilization of the server, and finally we're interested in the probability that there are 0 entities in the system. So we can easily find these things under the mmc assumptions that the arrivals are Markovian and that the service is also Markovian. You can see that I have the table of formulas extracted from the Modeling and Analysis of Manufacturing Systems book. And so the Python module, mmc.py, essentially implements this set of equations. Note that in order to solve for the values of interest, we need to know 3 things. We need to know the capacity C, we need to know the arrival or service rate mu, and we need to know the arrival rate lambda. And so those 3 characteristics define an MMC queuing system. For our Python module, there are basically 3 general ways that we can use the module. First, we can execute directly from the command line. We can execute from within the Python interpreter, or we can import the module into our own Python code. So look, we have the command prompt here. First use is, just as I said, directly from the command prompt. So we can simply execute mmc.py, and then the module will give us the syntax. So you can see that it takes 2 or 3 parameters or arguments, either lambda and mu or lambda, mu, and c. So we can do mmc.py 0.911, for example. It gives us an MM1 queuing system with then a lambda arrival rate of 0.9 and a service rate of 1. We can also leave that second argument off, and the third argument off, and it assumes a value of 1. So we could also change. So if we want to evaluate a MM4 queuing system, for example, we can simply execute it again from the command line that way. If we want to use from within the interpreter, use the module within the interpreter, we can just enter the Python interpreter, and we want to import from the MMC module. There are 2 functions of interest for us. Let's see, from mmc import, we first want to implement or import the mmc function itself, and secondly the function named show. In just a second we're going to look at this code, but we can basically import those, and to execute mmc we simply define a solution. Solution equals mmc 0.9 lambda mu c. And so the solution then that gets returned to us is a dictionary. So it returns a dictionary with the key value. So let's look here. Solution keys. If we want to see the key values, we can see that we have the input parameters, lambda, mu, and c, and then we also have the values that we solve for. We can use the show function if we want to have a more human-readable version of the solution. So again, we can use the mmc function and simply give it the parameters, 0.9, let's do 0.25 and 4 like we did on the from the command prompt, and you can see that it returns the values to us in the form of a dictionary, I mean. You can see the code is quite easy to use. Let's now have a look at the code itself. So the module includes the functions we just talked about, the mmc function and the show function. There's also a main function that lets us execute from the command prompt. And so you can see that we have the default value for the number of server C, and then we check for command line arguments, and we simply execute the mmc function with the input parameters and then show the solution. And so obviously the line here, line 82, is what allows the Python to the main module to execute if you were running this from the command prompt. So let's go back and look. These functions are pretty straightforward. We basically have the parameters lambda, mu, and c, and we define our dictionary, SOL, using the original values of lambda, mu, and c. We then float the arrival rate and the service rate, and then we make sure that the c value is an integer. It's just a quick note here from a Python perspective. When I was developing this module, I didn't make this conversion initially, and then the Python integer math became a little bit problematic, and so I'll talk more about that here in just a second. So we make floats for the lambda and mu and c. We can then calculate the utilization. We then store that value in our dictionary under the using the key row for utilization, and then we have to decide, is the system stable or not? In other words, is the utilization strictly less than 1? If it's not, then the system is unstable and we can't do any more computations. If it is, then we have our two cases. So you go back to our formula. You can see that our formulas are divided by based on MM1 and MMC. And so in our code, we simply test, are we an MM1 queuing system here? If so, then we have the set of calculations for probability of 0 in the queue, number in the queue, number in system, time in queue, and time in system. Otherwise, we have an MMC queuing system, and so we're doing a little bit more complex calculations, but again, very straightforward calculations to solve for these values. So as I mentioned in the beginning, I ran into some problems when I was developing this module before I converted the lambda and mu into floats, and that problem appeared right here in this calculation for the number in system for an MMC system. You can see that we take the number in Q and then we add L over mu. And it turns out if you have integer values for L and M, then Python by default is going to use integer math. And so for example, if I have 3 over 2, it returns 1 rather than 1.5. And so I ran into that problem, and it actually took me quite a while to figure out what was going on. But once I've floated those values, then we of course get the correct math. The show function simply shows in a human readable form the queuing system solution. And so one thing of interest here is that we have an optional parameter for solution, for title. And so when you execute the code, you can either give it a title or it will just show a solution. So it will let you, if you're solving multiple queuing systems, it will let you give each one an individual name. And that's it. That is the entire module. You can see it's pretty short. It uses the factorial function from the math module, and other than that, it's a very simple set of calculations. The final use of the Python module is within your own Python code. So rather than the command line from within the interpreter, we would then import the module into your own code. And I'm going to leave that as an exercise for you to explore.